Hello everyone, and welcome to Calculus. Today we're going to be studying slope fields. An equation involving a derivative is called a differential equation. Differential equation. In college I took an entire class called Diff-EQ, which was differential equations. So learning how to solve all the ones that we don't learn how to solve in calculus. There's so many more that don't fit into this beautiful little mold that we've been creating for you. But let's talk about the ones that we do know how to solve. If we're given an equation like this, I can move the dx to the other side. I can integrate both sides. And the integral of just dy is y. And with respect to x on this side, the integral of secant squared is tangent of x. And 2x is going to be 2x squared over 2. So I'm just going to write plus x squared plus 5x. Remember, the derivative of tangent is secant squared, so this is just needs to be one that you either have memorized or have on your appendix. And then, of course, we always add plus c. We do that because there's an entire family of functions of the form y is equal to tangent of x plus x squared plus 5x that all have the same derivative. So this is considered a general solution. When you write plus c, that's considered a general solution. But sometimes we want a particular solution. So instead of just saying, well, I know it's one of these graphs, but I don't know what C is, if you give it a point and say, no, I want it to go through the point 1, 0, now you can actually find an answer. So let's go ahead and do that. Again, I'm going to put my dx on the other side, integrate both sides. The integral of dy is y. The integral of e to the x is just e to the x. And the integral of 6x squared is minus 2x to the third. And I'm going to write plus c. So to find c, I plug in my 0, 1. So the 0 goes in for the y. Sometimes people do it backwards by accident. Is equal to e to the first minus 2 times 1 cubed. This pen is giving me trouble today. Plus c. So that gives me 0 is equal to e minus 2 plus c. So c is equal to 2 minus e, which means I have a final answer of y is equal to e to the x minus 2x cubed. Then again, my c is 2 minus e. Okay? That is called a particular solution. So sometimes they will call this kind of problem an initial value problem. You don't have to memorize that or anything, but it should be obvious. They gave you an initial value. And again, then it would have a particular solution. So the green is the general solution, but then the red one is considered a particular solution. So a particular solution, find the particular solution to this one whose graph passes through 0, 3. You should be able to do this one on your own. If we were in school, I would not be doing this one for you. So stop the video, do it on your own. All right, and of course now I will do it for you. I'm going to integrate both sides, and I get y is equal to 2x squared over 2, so just x squared. Again, secant squared, got to have this one memorized. The derivative of tangent is secant squared. And then my plus c, I'm going to plug in my 0, 3. 3 is equal to 0 squared minus tangent of 0. Need to know all your trig functions. You need to have them all memorized or on your appendix. Tangent of 0 is 0. So c is equal to 3. Which means that my final answer is y is equal to x squared minus tangent of x plus 3. So I realize that so far this is all review, and we have one more review problem to do before we actually get to slope fields. This is from a couple videos ago. This was the fundamental theorem of calculus. See if you can do it. See if you can find the solution to the differential equation for which f of 7 is equal to 3. So you may try to just integrate it, but hopefully you'll see right away that if you let u be equal to negative x squared, which is the only way for you to integrate e, you can only integrate e to the u. You don't have the du. You don't have that extra x. You can always add a constant, but not a variable. So this is going to be something you can't integrate. So our little workaround for this is to say, well, I want to integrate e to the negative x squared, but I can't. So I'm going to put my known value down here and my x up there. And then you always have to change the variable. So instead of an x here, because you can't have an x in both spots, I'm just going to call this negative, let's use w, negative w squared dw. That would give me capital, actually not capital. So let's actually talk about this for a second. Normally we do capital F of x, and then if we take the derivative, we get f of x. And if we take the derivative of that, we get f prime of x. So we're usually working, when we do integration, we start at f of x and we integrate and we get to write capital F. But in this case, you're starting at f prime. So if you start at f prime and you integrate, you're actually going to be at f. So this is going to give you f of w minus f of 7. Sorry, f of x, because you would plug the x in. F of x minus f of w. And then I add the f of 7 to the other side. From 7 to x of e to the negative w squared dw, and that will give you f of x. But we don't really want f of 7. F of 7 is equal to 3. So by changing that to a 3, you've done a little sneaky workaround. You've given me a function that I can figure out any value you give me by using my calculator, even though I wasn't actually able to integrate it. And this is from a couple lessons ago, the fundamental theorem of calculus. So there's like a little summary of all the things we learned. First, we learned how to use just plus c. Then we learned how to do a particular solution where we found c. Then we learned this little sneaky workaround. And today is going to be the final method for finding the integral of a function. So let's say you start with the differential equation dy dx is equal to cosine. I know you know the answer. The answer is sine of x. But let's say you didn't know that. I want to start with a known one, and then we'll do an unknown one in a minute, just so that you can see how somebody figured this out. It's actually very cool. So if you only knew a derivative and you didn't know how to integrate it, instead of using this little tricky workaround that we did, you could graph it. So I'm going to make a chart, and I'm going to put x here, but instead of y, I'm going to do dy dx, which remember means slope. So when x is equal to 0, cosine of 0 is 1. So I'm not going to plot the point 0, 1. Instead, at 0, I'm going to make a slope of 1. At 0, I'm going to make a slope of 1. Now, it doesn't say what the y-coordinate is. So interestingly, you're going to have to make a slope of 1 everywhere. Now, there's actually ones in between too, but that's going to get a little bit cluttered. So we're just going to make them at the integer coordinates. So there's my slope of 1. What's another value we know for cosine? We know cosine of pi fourths is the square root of 2 over 2. That one's not very convenient, but I do want you to learn it. So 1.4 divided by 2, 1.7. So almost 2. But it's a slope. So you're just trying to draw a slope of 2. So at pi fourths, I'm going to make this a little bit steeper than I did the 1. Okay, a little bit steeper than I did the 1. Doesn't have to be perfect, just as long as it's steeper than your other slope. Pi halves. At pi halves, oh, this is an easy one to graph, right? 0. So what I'm saying is that at pi halves, the slope is 0, not the y value, the slope. In fact, we don't know the y value. So at any y value, the slope is 0. Let's keep going with our chart. X, dy dx. Let's just do the easy ones. So at pi, we know the slope is -1. So at pi, the slope is -1. At 3 pi halves, the slope is 0. At 2 pi, the slope is 1. And I'm doing it for all the y's because it doesn't say anything about y. We'll do one where y is included in a minute. So how can you figure out what this means? Well, somebody looked at this graph and the ones, in between, if you did every single one and said, hold on, as a general shape, I can see that this is going up and then it's going down and it's flattening out and then it's going up again. What have I just drawn? I've just drawn sine. So graphically, somebody figured out that if the slope is cosine, then the original graph must be sine. All right, so we're going to try that on one that you don't know the answer to, and hopefully it'll make a lot of sense. This time, though, I'm going to need 3 columns, x, y, and dy dx, because the slope changes based on both x and y. So let's do the easiest point, 0, 0. Ooh, but I can't, because 0 divided by 0 is undefined. You can't divide by 0. So the slope is undefined at every y0. So I could do 1, 0, 2, 0, 3, 0, -1, 0, and they would all be undefined. So because there's a million points to plot, you're definitely going to have to look for patterns like this. So at 0, 0, or any y is equal to 0, which is pretty much the whole x-axis, the slope is going to be undefined, which if it helps, you could maybe draw it straight up and down. That is what an undefined slope is going to look like, except right at 0 over 0. That's even more undefined than normal undefined, okay? But typically a number divided by 0 would be a vertical slope, like you learned way back in Algebra 1, a long time ago. Okay, let's do a different point. Let's do 1, 1. So if x is 1 and y is 1, then the slope is -1. So right here at 1, 1, I'm going to put a slope of -1. Now you got to look for patterns. The same is going to be true at 2, 2, 3, 3, 4, 4. But you're not going to want to actually write all those. So 2, 2 is going to have -1, 3, 3, 4, 4, 5, 5. Okay. Even -1, -1, -2, -2. -1 divided by -1 is 1, but there's that negative out in front. So it's also going to have a slope of -1. That's how you fill in a slope field. You definitely do not want to plot every single point, just enough to give you an idea of it. Let's do -1, 1 over here. Does it produce the same thing? No. -1 divided by 1 is -1, but because of this negative on the outside, it's actually going to turn positive. Does that keep working? It certainly does. -2, 2 will produce a -1, but with the negative out in front, it turned to +1. So a lot of times, once you get one thing going, you can kind of get a whole bunch of it. Now, is this something that you recognize? Probably not yet, but soon. Wait for it. And as soon as you get it, great. All right, let's do, so we know all the y's equal to 0 is bad. What about when all the x's are 0? 0, 1. Well, 0 divided by 1 is 0. 0 divided by 2 is 0. 0 divided by 3 is 0. 0 divided by -1 is 0. So it's going to have a flat slope in all these spots. Again, don't clutter your table with it. Maybe just leave the first one that you were thinking about. Still don't know it? Okay, so you are required to make a point at every single spot, at every integer coordinate. So let's do another one. Let's say what happens at when x is 2, 1. Well, at 2, 1, you get -2. All right, so here's the rule for me and for the AP exam. You don't have to be able to perfectly graph a slope of -2. You just have to graph it steeper than a slope of -1. So since this is a slope of -1, I need to make this one steeper. Okay? So now there's not as easy a pattern going on here. Let's do 3, 1. That's going to have a slope of -3. I need to make it steeper and steeper and steeper. And then the same is going to be true for this. This is going to be +1, +2, +3, +4, +5. It's getting really steep. You see how I'm making this pattern here? Let's go in the other direction. I know you're thinking this. You're kidding me, right, Mr. Shaffer? This is so tedious. You'll get better at it. I'm just trying to be very thorough on this first one to make sure that you get it. Let's do x is equal to 1 and y keeps changing. So when x is 1, we already have the 1, 1. What about at 1, 2? Then it's -1/2, which means it gets shallower. And then at 1, 3, it's -1/3. Shallower, shallower, shallower. Okay, that one might have done it for you. Did that one do it? I'm going to do the ones on the opposite side. So here's my +1. Now it's only +1/2, +1/3. Starting to see it yet? Okay, it's a circle. Like that. So making sense? How could we have actually done this one by hand? You actually could have done this one. You didn't need slope fields to calculate this one because we did learn separation of variables. So you could have put the y with the dy is equal to the x with the dx. You could have integrated and gotten y squared over 2 is equal to -x squared over 2 plus c, which if you multiply through by 2, you still would have plus c. It would just be a different number now. But if you move the x squared over, x squared plus y squared is equal to 2c. So some radius, okay? Which, of course, that's the whole point, is that we don't know this radius. So how do these connect? You might be looking at this saying, well, this one doesn't connect to this one perfectly. I'm going to have to make them all bubbly. But not really. It's just that this one doesn't necessarily go with that one. Maybe this one goes with this one, goes with this one, right? You do want it to be a nice circle. So like that. So it doesn't necessarily connect the ones you think it's going to connect. So did that one kind of work out? Yes, but then this one didn't. I wasn't shooting for that one necessarily. But it does make a circle. So somebody took this differential equation, maybe somebody that didn't know how to do separation of variables, and said, well, I don't know the answer. I don't know what to do. I can graph it until I figure it out. So it's a really neat concept, taking the graph of the derivative and calculating the integral that way. So if we were in class, I would totally give you the rest of the class to do all of these problems. I would not teach anything else on the board. So my best advice to you is for you to turn off this video and see how many of them you can do. What would be even better is if you got on Zoom with a classmate and tried to do it together and chalked it out and took pictures as you went. But that being said, I will now do each one for you so that you can see how I would do it. So this one only has an x in it, so I don't need to make a y column. So when x is 0, I get 1. So that means at 0, it has a slope of 1. Notice there's many fewer dots than on the last one because you do have to have something for every single point on these. So I have 1, but there's no y, so it's going to be 1 for all of them. So you're going to fill in these dots pretty quickly. At 1, it's going to be a slope of 2. So how do you make a slope of 2? You just have to make it steeper than the 1. At 2, it's a slope of 3, steeper than the 2. And you don't have to keep making the table if you're like, I can tell what's going to happen. It's getting steeper. Then just draw it. At -1, should you make it even flatter? No, all the way flat. Okay, do not be too presumptuous. You do have to find some points. So at -1, it's totally flat. And then at -2, the slope is -1. Try and make them look the same. So whatever steepness, so let's see, mine was a little steep. You do want to make it the same steepness as your +1, so they match, so that there's symmetry there. And then at -3, the slope is going to be -2, which is steeper. And what do we get? And this is what I mean. You do not have to do anything else. This problem is done. But I don't want you to think that you're trying to connect these three. Like, you're not trying to connect those three. They don't go together. Instead, these might go with that one, right? But you see what I mean? The flat line, there's flat lines all the way through here. We just didn't draw them all. So you can't necessarily look at it and think, I have to connect these. You're just looking at it for a general shape. And if somebody did this problem and really didn't know how to integrate this, which of course would be silly. I mean, it's just x squared over 2 plus x, right? But if you really didn't, you could see now that it's parabolic in shape. That should make sense. Oh, yeah, look at that. I know it's going to be a parabola. And sure enough, it looks parabolic. And if you factor out the x, then you can see that it shifts. Well, I guess not really from that, but you can see that it shifts to the left because this is positive. So whatever this other, point is, it's not necessarily x because there could be a shift up or down. But I want you to see that it definitely shifts to the left. Do you have to do any of that? No, you just have to make the slope field. All right, this one's new. This one's in terms of y. So now I'm going to make my chart with a y and the slope. When y is 0, we get 0. So y0 is all along the x-axis. So 0, 0, 0, 0, 0, 0, 0. See how fast I can fill them in? At 1, the slope is 2. So never got to do a slope of 1. I'd have to do 1/2, which I'm not going to do. So at 1, y is equal to 1. The slope is pretty steep. It's already 2. And when y is 2, the slope is 4. So as long as you make it steeper, you're okay. At -1, the slope is -2. So I need to make it the same steepness, but in the other direction. And at -2, the slope is -4. So even steeper and negative. Pretty cool looking, right? Okay, this next one's a hard one. How do I know it's going to be hard? Because I see an x and a y. So the two that we got to start on only had an x. So when I figured out x, I got to make the entire column of y's. And this one only had a y. So as soon as I did one y, I was able to do the whole row of y's. This next one has an x and a y. And just by nature, then that makes it a lot more challenging. So I have to make an x column, a y column, and a dy dx column. And truth be told, these are just plain tedious. So I do try and look for places where there's zeros. Zeros always seem easy. You don't have to worry about the slope of them. They're just flat. So at the coordinate point 0, 0, it's 0. If these were opposite, like 1, -1, 1, -1, 0, 2, -2, 0. So 2, -2. And then I think, oh, I bet this goes in a diagonal. So sure enough, -1, 1, 0. And I'm not even going to bother to do the next one. I feel that confident about it. So people that are in AP, just so you know, when they grade these, they usually make the slope field a 2-point problem. And the first point is for getting all the correct 0 spots. And then the last point is for all the other spots. So if you can just get those 0 spots, you've already gotten half the points for it. But we do need to get some more. And This pattern is definitely a little bit tricky. I would just plot a lot of points, and eventually I think you'll see it. So obviously I picked the easiest numbers. I'm going to do all the zeros. So when x is 0 and y is 1, I get 1. But 0, 2 is going to be 2. 0, -1 is -1. And then 0, -2 would be -2. You don't have to write them all down once you've got some pattern. I'm going to do, that one worked out really well, so I think I'm going to move over a column. No, I'm going to do all the y is zeros first. So when y is 0 and x is 1, so x is 1, y is 0, that gives me a slope of 1. 0, 2 gets a little steeper, which means 0, 3 will get steeper still. 0, -1 will give me a slope of -1. I just want to try and repeat that one in symmetry. And obviously 0, -2, steeper, and then 0, -3. So I feel pretty good about the ones that I've gotten so far. Unfortunately, I'm just going to erase because I need the space. I realize on your paper, it's just tedious. So I picked the smallest numbers possible. We'll do 1, 1, which will be 2. So this was a 1. Now this is going to be a 2. 1, 2 will be 3. Right? Do you see that? And that's going to happen with this one too, when I go up the y. Because think about it, if y keeps getting 1 bigger, whatever x you're at, it's just going to get steeper and steeper. So whatever this is, steeper and then steeper. So what about down below it? So this is 1, 2, 3, -1. 3, -1, less steep. So a little less steep and then a little less steep still. So can you fill this one in without actually finding its ordered pair? Probably, if you just look at it like that. Let's do some in the negatives. We already have 2 of the x is equal to -1. Let's do -1, 2. So -1, 2 is going to give me a slope of 1. And then -1, -1 will give me a slope of -2. So a little steeper. -1, -2 will give me a slope of -3. So steeper still. Okay. So you might look at this and say, I can start to figure it out, but this one honestly is just really tricky in my opinion. So now let's do x is -2. So we know that when y was +2, we had the 0. Remember that up there? That line is way up there. So let's go down to -2 and then 1. That would give me a slope of -1. Now I already have this one. That's supposed to be a slope of -2. So if this is a slope of -1, you have to make it a little bit more shallow than that one. And then you can make it steeper and steeper. Let's go over to -3. -3, I already have 0, so this must be a slope of -3. So if I go up 1, I'm only at a slope of -2. So this one needs to be a little shallower. And then this one is going to be a slope of -1. Oh, and now I see these lines are all the same. So, except that one that I didn't draw quite the same. So these were all the same. So hopefully you're seeing that. It's got that nice curvature. And then this gets steeper and steeper. Now that you stand back and look at it, hopefully you can see it just a little bit better. It's nice curving shape, but definitely a hard one. All right, so let's do 4 and 5, which are going to be our 2 lovely, easy ones. How do I know that? Because there's just an x, and dy dx is just times 2. So all the zeros, when x is 0, it's going to be 0. When x is 1, the slope is going to be 2. So at 1, I'm going to have a slope of 2. At 2, I'm going to have a slope of 4. I just need to make it steeper looking. And then at 3, it needs to have a slope of 6, which it's hard to even draw it much steeper. So try and make it just a little bit. At -1, slope of -2. Negative 2 is going to be a slope of negative 4. I just need to make it steeper than the last one, and then steeper still. Look how much faster that one went. Okay. And of course, could you just integrate this one? Yeah. If you move the dx to the other side and then integrate, you can see if you got the expected answer. 2x squared over 2 is x squared. Doesn't that totally look like x squared? So if you were to come down, look at that, plus c. Okay, it definitely makes a parabola. Do I want to do that? I do not. Do not draw in your slope field unless they ask you to, which will be next. So not all of them are as tedious as number 3. Number 5 is going to be a nice one because it only has y's. Now think about it. How do you expect the answer to look? X's are going to look the same vertically. Y's are going to look the same horizontally, backwards of how you might think, but consistent with y is equal to a number, like y is equal to 3, isn't that a horizontal line? So when y is constant and x varies, then it's going to be the same horizontally. So when you see that y is in the equation, it kind of gives you a hint as to what it's going to look like. So, oops, I put the x there. Y. Have it. All right, so when y is 0, I get negative 1. So all the way across, negative 1. That's where y is equal to 0. When y is equal to 1, I get 0. Okay. When y is equal to 2, I get 1. Try and make this the same level of slope that you made the negative 1. When y is negative 1, I get negative 2. So make it steeper than that negative 1 slope. And of course, negative 2 is the last row we have to fill in, which would give me a slope of negative 3. And as long as you make it steeper still, it'll be considered correct. But now that you step back, you're finished. Can you see that shape? I hope so. All right, last pain in the neck one. So I'm going to make 3 columns, x, y, and dy dx, which is negative y over x. So this time, what can't x be? X can't be 0. So there is a vertical line at all the x is equal to 0. And then, so x is equal to 0, undefined, no matter what y is. And then when y is equal to 0, no matter what x is, no, so I'm just not going to fill it in. It's going to be 0. So all of these spots are going to look like this. So how can that be true right in the center? Well, 0 over 0 is just undefined in general, so don't put anything there. All right, so now let's do some nice easy points. When you have the two numbers the same, 1, 1, 2, 2, 3, 3, that's always going to produce a slope of negative 1. So 1, 1, 2, 2. I don't have 3, 3 on there. Negative 1, negative 1, negative 2, negative 2. Then what about if we make them opposite? So 2, negative 2 would make negative 1, but since it's negative, it'll actually end up being positive 1. So whenever these are opposite, so 2, negative 2 will produce 1, 1, negative 1, negative 1, 1, and negative 2, 2. Okay, so you're starting to see something? So sometimes kids stop here and they're like, got it, it's a circle. Is it a circle? It is definitely not. I know we had a circle earlier, but look at these points. That doesn't connect your slope field, not at all, okay? If they were this way, that would make a circle, but they're not, it's opposite. So how's that gonna affect it? You might just have to do some more points until you get it right. So what points haven't we done? We haven't done 1, 2. So at 1, 2, x is equal to 1, y is 2, negative 2. So this is negative 1, this is -2. Look at that. Okay, it's a little steeper. And then going out, so this was 2, 2, that gave me 1. And if I go all the way out to 3, 2, then I'll have 2 over 3 negative, so it's shallower than 1. So it's going to look like that. So it's going from steep to shallow, steep to shallow. Hopefully you're seeing it now. This is going like this and then shallower. This is going from steep to shallower. This is steep. And then if you're not sure, you can do another one. 1, -2. So when y is 2, now it's +2 over 1. So steep, less steep, and then shallower, and then shallower. Okay, so you don't have to necessarily plot every single point, but you might want to keep checking. Like as I enter a new quadrant, I'm like, okay, hold on, let me just check. I'm at -2, -1, which would be 1 over 2, which would be 1/2 positive, but -1/2. So shallower, and then shallower. But then this one, steeper. So that's what it would end up looking like. So a little bit tedious, but in the end, I mean, you get to draw in math. That's kind of fun. All right, so this is matching. You can go ahead and try and do it on your own. So what they're saying is somebody had some kind of derivative equation, and this is what they ended up with. What does it look like to you? We're just trying to get you to see if you can look at this and say, oh, I can look at that and know what that is. Okay, if you're not sure, go to one that you do know. You might sit there and say, oh, I see this one. This one is some kind of parabola. Is there a parabola on here? Just the one. So I would say that number 9 is C. This one is just a straight line, like y is equal to a number, right? So is there anything that's like that? There it is. Number 7 is D. If you're getting the hang of it now, you might want to stop and see if you can do it on your own. Another one that's very familiar, a straight up line. So which one is that? It would be 8. If it helps you, think of it as y is equal to x plus c. It's a line that's clearly been, the family of functions is all of them. So that might help you think about it. But number 8 is going to be h. Let's see another one. Well, this is definitely some kind of a trig function, right? It's going up and down, up and down. Ooh, but there's sine and cosine. So I see another trig function. How do I know which one is which? Because this one has the attributes of sine, in that at 0, it has a slope, where cosine at 0 is flat. So this one is going to be my cosine, B, and this one is going to be my sine, E. So natural log, I don't know if you remember what natural log looks like, but natural log normally looks like this. Remember, it's the inverse of an exponential function. This is an exponential function. And then if you graphed your y is equal to x line, this would be a logarithmic function. So when you see ln, you need to be thinking about this graph. But you might be looking through going, but I don't see that graph. Well, it is right here, okay, some family of them. How do you get the opposite ones? That's been caused by that absolute value. That absolute value allows you to also, because normally you can't take the log of a negative number. So that's where that comes from. So G is going to be the answer to 14. Let's see, what do we have left? A cubic, and then a function with a rational function. But this one's our cubic. I don't know if you can see it. Notice I didn't actually hit a point right there. I didn't try for one of those two. It's just a general shape. Can you see the general cubicness of F? That's what that one's supposed to be. So by default, we're going to put an A for this one, but you should also recognize that this is going to have a vertical asymptote at 0. And sure enough, it does. This one is one of these graphs. I know you're used to rational functions doing something like this, but if it's squared, it makes them both go up. Okay, now we're going to do something opposite this time. This time, you're not looking at it and saying, oh, I can figure out what that is. This is a circle. I'm going to look for one of the answers that says x squared plus y squared is equal to a number. None of them say that, because this time they're giving you the derivative. So be really careful that you understand the difference between the two. On this one, they're saying, if somebody showed you this slope field, you could tell them what the function must be. This one's just letting you not have to do it yourself. This one is saying, if you were to make a table, which one of these would you get? So there are definitely tricks to it. This one clearly has x's and y's. So it's either going to be 17 or 18. This one is the same in vertical strips. So this one should only have an x. So by default, that makes this one b. But another way to really check it is that if you were to integrate it, then you would get x squared over 4 plus x, which is some kind of parabolic function, and it looks parabolic. So there's a couple different ways to think about it. This one only has a y, which means it should stay the same all the way across, just like when you have y is equal to 5. That's a horizontal line. When you just have a y, it should be horizontal. It should be the same all the way across. So this one must be D. See some of the little patterns we're finding here? So now you have 2 left, right? But this one, clearly, whenever x is equal to 0, it comes out to be 0, which is good for this one, because if x is 0, it will be 0. And whenever y is 0, it's undefined. See that? You can't have y, this is the line y is equal to 0. You can't have y be equal to 0, so it's undefined. So that's how I know that this one is A. Notice I haven't actually made my table. I didn't even plot the points. This one is saying it's 0 pretty much at like 1, 1, 2, 2, 3, 3. How would that happen? If you're on this one, 3 minus 3 would be 0. So I didn't actually need to make points. So matching is definitely easier than drawing your own, where you have to make look at this one. It's almost the same, right, as this one right here. But it was so nice just to have to match instead. So B, D, C, A are the answers. All right, the calculator drawn slope field for the differential equation dy dx is equal to xy as shown in the figure below. The solution curve passing through the point 0, 1 is also shown. So they're saying if I tell you that 0, 1 is the solution, then even though there's all this downward stuff, this is the one you would follow. That makes the most sense. What if the solution curve needed to contain 0, 2? If instead of 0, 1, it contained 0, 2, then I would have drawn it like this. Hopefully that makes sense. Or if they said the solution curve contained 0, -1, then I would have drawn it like this. Now look, I'm not even going to hit a point. I'm not going to hit any single line they drew, but I'm following the pattern of it. That's the goal. You shouldn't try to make it fit onto their things. That's not the point at all. Is to sit there and say, oh yeah, I can see the curvature of this graph. So if I told you that this was my derivative and it passed through the point 0, 1, 0, -1, then the red line would be the answer. See if you can try that on your own for the next one. This is the calculator drawn slope field for dy dx is equal to x plus y. What would the solution curve look like if you had to pass through 0, 1? What do you think that would look like? Okay, please, please, please try to do it on your own. Okay, so if you're turning the video back on, it clearly has some kind of an asymptote, oblique asymptote, and then it goes up like that. That's how I would draw it through 0, 1. And if they said that the solution was being done through -3, 1, 2, 3, 0, then I would draw it something like this, maybe. Okay, something slightly curved. Looks like it's going to follow the asymptote in the end and then veer off down there. And that is slope fields. So there is a homework worksheet that you can practice slope fields for yourself. And if we were in a normal year, this would be the point at which we would end our integration unit, and there is 1 unit left. Have a great day.